Ever wondered how to traverse a maze, or perhaps how web crawlers work to index web pages? The answer to these questions lies in a fundamental algorithm in computer science known as depth-first-search, or DFS, as it's commonly referred to. In the next 7 minutes, an exploration of the DFS algorithm will unfold, revealing its steps and key points. Imagine standing at the entrance of a complex maze. The DFS algorithm is similar to the strategy you might use to navigate through it. You choose a path and follow it as far as you can. If you hit a dead end, you'd backtrack to the last junction and choose a new path, repeating this process until you've explored the entire maze. In computer science, a similar approach applies when traversing data structures like trees and graphs. DFS starts at the root, or an arbitrary node in case of a graph, and explores as far as possible along each branch before backtracking. So how does DFS work step by step? First, select a node. If it's a tree, start with the root. For a graph, you can select any node, mark this node as visited. Next, move to an adjacent unvisited node. Mark this new node as visited. This step is repeated, moving deeper into the structure until a node with no unvisited neighbors is reached. Now it's time to backtrack. Return to the previously visited nodes in order to find unvisited nodes that can be explored. This process continues until all the nodes have been visited. It's important to note that DFS uses a data structure known as a stack to remember the nodes to be visited. The key points to remember about the DFS algorithm are: first, DFS is a recursive algorithm. It explores as far as possible along each branch, then backtracks to explore new paths. Second, DFS uses a stack to keep track of nodes. When a node is selected for exploration, its adjacent unvisited nodes are added to the stack. If a node has no unvisited neighbors, the algorithm backtracks by popping nodes from the stack. Third, DFS is not the fastest search algorithm, but it's excellent for tasks like maze solving and topological sorting. It can also be modified to solve other problems, such as finding connected components in a graph. Fourth, while DFS is powerful, it's also important to understand its limitations. For instance, in a large graph, DFS can consume a lot of memory as it keeps track of all visited nodes. Moreover, it might not find the shortest path between two nodes. In conclusion, DFS is a fundamental algorithm in computer science with a wide range of applications from web crawling to maze solving. It's an algorithm full of depth, just waiting to be explored.